9 questions for homework last night. Practice question set number 29. Almost done. Just a couple more of these, and then that's it for us for the year here. 9 of them, so a big one this time. Starting with question number 1, talks about this unstable nucleus that's formed up here as a result of this artificial transmutation. Look what's happening. An alpha particle, high-speed alpha particle that is directed at a nucleus that has a relatively small atomic mass. The alpha particle becomes part of the nucleus, and then it produces a nucleus that's unstable. So we've got this taking place. The beryllium-9 being struck by the alpha particle, producing an unstable nucleus, and then we have an unstable nucleus emitting a neutron, producing a stable nucleus. So kind of two things going on here, right? There's the first reaction that causes the unstable nucleus to be produced, and then you get the secondary thing that takes place as a result of the first thing that causes the stable nucleus to be produced. All right, we're looking for what it is that's produced as a result of the first stage here, the unstable nucleus that's formed. So let's write a transmutation equation for this. We've got beryllium-9, which has an atomic number of 4. It's bombarded by an alpha particle or struck by an alpha particle. Is this alpha decay? Would we call this alpha decay? No, this is an artificial transmutation equation because it's alpha on the left-hand side. We're striking the beryllium with the alpha particle. We're producing a new unstable nucleus, a single unstable nucleus, which is going to be what? 4 plus 9 is 13. 4 plus 2 is 6. Looks like it's going to be carbon-13. So the answer is either going to be C or D. And then something else happens, right? Then you get a neutron that's released from the carbon-13 to produce an unstable nucleus. We'll worry about that later if we have to, okay? Two different things going on, though. We're just looking for now at the first one. All right, next question. Next part of the question says the physics principle used to determine the atomic number of the stable isotope. So we're trying to determine what this 6 is, this atomic number right here. Is it going to be conservation of nucleons or conservation of charge? What's a nucleon? We were talking about fission fusion yesterday. We defined a nucleon. Philip, what's a nucleon? Yeah, it's a proton or a neutron. So if we're trying to balance the protons and neutrons together, in other words, the nucleons, we'd be doing that up here, right? That would be conservation of nucleons. We got 13 nucleons on the left-hand side. We have 13 nucleons on the right-hand side. If we're balancing, well, we usually think of it as protons. If we're balancing protons, then we're going to make sure 4 plus 2 is 6, and then 6 on the right-hand side. But strictly speaking, we shouldn't say by rights that we're balancing protons here, because sometimes a proton will change into a neutron and a positron, or a neutron will change into a proton and an electron. So we're not really balancing protons per se, but rather we're balancing what? Charge. This is a charge, this nucleus has a charge of plus 4. This has a charge of plus 2. We got to balance the charge so that this has a charge of plus 6 on the right-hand side. So what's our answer here? C or D? Conservation of nucleons or conservation of charge? It's D, conservation of charge. If we were asked how we find the mass number, then we would say conservation of nucleons. If we're asked how we find the atomic number, then it's conservation of charge. Okay, number 2 says, if the new unstable nucleus is at rest when it decays, then what's the recoil speed of the final stable nucleus? So we got this carbon-13 that's at rest. It decays into an unstable nucleus and this neutron. We're going to say, I think, conservation of momentum. Pi equals Pf. The initial momentum of the carbon-13 would be 0. The final momentum would be m1 v1f plus m2 v2f. We're going to say this one's the mass of the neutron times the velocity of the neutron, which I think was given to me up here. 2.18 times 10 to the 7. Plus the mass of the stable nucleus, the thing that's produced in the end here, which they gave to me is 1.99 times 10 to the minus 26. And then we're going to solve for VF, okay, the final velocity of the stable nucleus. And I believe we got 1.83 for that. 1.83 times 10 to the 6 meters per second. You know what's funny about this question? Some of you last night as you're working on it probably struggled with this. If I gave this back to you or gave this to you back in February, You guys would have nailed that question. You guys probably got worse on this question. The reason you probably got worse on it, though, is not because it's harder now than it was then, not because you're not as smart now, it's just because it's been a long time since you've really done this stuff, right? Hopefully, come final exam time, hopefully you've gone back and reviewed all this stuff so that this stuff is a little bit more familiar to you. Josh, question? All right, so what's the law now? Is it conservation of energy or conservation of momentum? It's pretty clear at this point that we use conservation of momentum, right? It's an explosion, right? Whenever we have a collision or an explosion, we use the law of conservation of momentum. Okay, next question. Gamma radiation is chosen for food irradiation because it... Why, how are we supposed to answer that? I never told you why gamma radiation is chosen for food irradiation. There's going to be some things like this that I don't tell you. I don't know what they're going to ask. So how are we supposed to answer this question? Well, let's think about what we know about gamma radiation. Is it safe and low energy? No, it's unsafe and high energy. So that's not why it's chosen. Is it the easiest form of radiation to produce? I would suggest probably not, given that it's a secondary effect or a byproduct of something else. So in order to produce gamma rays, you got to produce something else first. So I would say that it's the hardest one to produce, not the easiest one to produce. Penetrates into food through its packaging. Yeah, it's got a pretty high penetrating power, right? It'll go through several centimeters of lead, so that could be. D, poses no danger to the technologists doing the irradiation. It would seem to me that it would provide significant danger. Of course, those safety concerns would be mitigated by things that they do to make sure that they're safe. But if they're not careful, then it poses significant danger to the technologists. So that C must be the answer. We know that it does penetrate into the food through its packaging, and that must be why it's chosen to irradiate food. So the answer would be C for that. Number 4 and 5 goes with this information here. We have this prediction that radium would emit alpha particles, which we're familiar with, double alphas, which we're not familiar with. Don't worry about that. Hey, when this question appeared on the diploma exam, nobody was familiar with that. People are now because they do this question as practice, but at the time, nobody had double alpha. What's that? Well, they tell us, right? Triple alpha? Well, they tell us what a triple alpha is. So whenever they do that to us, whenever they give us something that we don't know about, they tell us about it. Don't panic about it, just deal with it. And then it talks about the number of particles and how long it's run for and so on and so on. We want to find out what's going to be observed in the greatest abundance here. Well, the greatest abundance is probably going to be alpha particles because it says it emits alpha particles and a few double alphas and even a few triple alphas. So it's going to mostly emit alpha particles. And if it mostly emits alpha particles, then we're going to balance this equation. What is radium? Is it 88? Is it atomic number 88? It produces alpha particles. Also these other ones, right? But those are separate reactions there. Plus what? 4 plus 219. 88 plus 2 is, 86 plus 2 is 88. That's going to be Rn right on. So that means that the answer is going to be A, right on 219. And the next question, which of the following products was not predicted by Rose and Jones? So we're going to do the same thing here, except that we're going to have to do it a few more times. We know the answer is not A because clearly that was predicted. Let's look at double alphas. 223, 88 goes to 84 beryllium plus, what is that going to be? 215 and 84. Is that polonium? PO? Okay, polonium was predicted then. All right, last one here. 223, 88. Radium goes to triple alpha particles. Triple alphas. What is that going to be? 12.6, I think it was. Carbon. Plus, what, 211. 82. That's going to be lead. Which means the answer is going to be no. Means that was predicted. that was predicted, right? And the answer is going to be D. How many people said C, actually? How many people made the same mistake as I almost just made? Anybody? Man, that would be an easy thing to make, eh? You get to that last one, and that's what we get, so that's what we circle, except that we're trying to eliminate there. The answer would be D. Next, we're getting there, guys. Almost done these set. Question 6, in the transmutation reaction above, an alpha particle is absorbed by nitrogen nucleus. There's an unstable nucleus, and then that decays producing a proton in an identified nucleus. The values of A and Z are going to be what? Listen, we got two things here, right? Just like we did in one of those other questions. There's this reaction, and then there's this reaction taking place. We want the values of A and Z, so let's see here. 12,7, nitrogen plus an alpha particle. It's an artificial transmutation equation, right? Goes to the unstable nucleus, which is going to be 16,9. And I don't know what 16,9 is. What's atomic number 9? Is it, what's after oxygen? Fluorine, that's right. And then fluorine decays into a proton. That's a proton, right? And something else. What's it? What else? 1 plus 15, 1 plus 8, 15, 8 is going to be our answer there. That's going to be oxygen, by the way, although you don't need to know that. Yeah, you could. Yeah, you definitely could skip the middle step. Did you guys hear that question? If we need to do something with the middle step and to figure out what that is, then obviously you can't skip it. But if you had 13 middle steps in there, you could go from first to last just fine, and you would end up getting the same thing, right? In the end, we got 16,9 right here. We have to have 16,9 right here, and we have to have 16,9 right here. So there's no reason why you couldn't go directly from this one to this one if they're not asking you anything about that middle step. Yeah, good point. And then we have some information about this Mars Pathfinder mission. We got to figure when you see this, probably going to have to balance that, right? What are they asking me here? Balance it. What's the values of A, B, C, D? 4 plus 23 is 27. 2 plus 11 is 13. On the right-hand side, 1 plus 26 is 27. 1 plus 12 is 13. So my answer is going to be 2612. Fill that in right here. 2612. Element X is going to be magnesium, is it? Atomic number 12 is magnesium from my periodic table. And then finally, the last question. The signals are sent to the Sojourner. The distance between Earth and Mars is what? It's from our last unit. We say D is equal to V times T. The speed is 3 times 10 to the 8. And the time is 10 minutes right here, or 600 seconds. That gives me 1.8 times 10 to the 11, I believe it is. So 1811. Whoops. 1811. Good there? Good? All right.